Today, we're very pleased to have our first CAMS of the semester, very first. And this is joint as a special colloquium where Ahmed Bou-Rabee from the Courant Institute, who is here for job interview purposes as well, will give us a talk on homogenization with critical disorder. Thank you.
Thank you for the invitation. It's great to be back in LA. I shouldn't really comment on what's happening around us, but hopefully for the next 50 minutes, we can just talk about math and forget about fires around us. So this talk will hopefully be accessible, and in case there's something that someone cannot understand, please interrupt, and I'll try to rectify the misunderstanding. So today I'm going to talk about homogenization. Homogenization is roughly the mechanism by which systems with small-scale disorder can be approximated on large scales by smooth systems, by nice systems. So the world around us is disordered and chaotic. For example, if we look at this table under a microscope, we'll see ridges and valleys, but to the naked eye, the table is flat. Homogenization is the approximation of a complex system by a nice simple one. So it's the mechanism by which this happens. For example, if we look at this sort of square here, we see a bunch of splotches of paint. We don't really see anything here, it's just disorder. So if we zoom out a bit, we see that those splotches of paint look like they're sort of part of a flower. And if we zoom out even more, we see this beautiful painting. This Seurat painting is on display at the Art Institute of Chicago. And it has this feature that if you take any square of the painting and you zoom in on that square, all you'll see is the collection of splotches of paint. And the colors that our eyes see depend in a complicated way on how those splotches of paint are arranged. So they depend on multiple small-scale factors like the dot size, the colors, the spacing between the splotches, and the placement. And the color that our eye sees, if we step away from the painting, depends on all of those small-scale features. And this procedure where our eye mixes together these small-scale splotches is called optical mixing. And it's supposed to generate more vibrant colors than what you would get if you took those different colors of paint in a paintbrush and just combine them together. But like optical mixing, like what our eye does for this painting, homogenization is typically not a simple linear average of the small-scale system. It sort of depends in a very, very complicated nonlinear way on the features of the small-scale system. So this Seurat painting is an example of homogenization in the real world. And now I'm going to talk about some mathematical models of homogenization, starting with what's known as simple random walk on a grid. So let's take an infinite square grid and start a walker at the center of the grid. And say that in each time step, the walker chooses between one of its four neighbors with equal probability and then moves to that neighbor. So here I've drawn the path of the random walk for 30 steps. So this walk is called simple because the transition probability, sort of where it moves, doesn't depend on where it is in space. And each of its neighbors has the same chances being moved to. We can take this model, simple random walk, and introduce periodic disorder in the following way. Take our grid, Z2, and color it blue and green according to a checkerboard. And say that on blue squares, the walk is more likely to go left and right than up and down. And on green squares, more likely to go up and down than left or right. So this is an example of periodic disorder. We can make this disorder random by coloring the checkerboard randomly. For example, we can, for each square in the grid, flip a fair coin. If the coin lands heads, color the site blue, otherwise color it green. And then run a random walk with the same blue-green transition probabilities as before. This is an example of random disorder, and we can have an even more drastic example of random disorder by taking the graph and removing vertices from the graph. So here I've taken Z2 and independently for each site in the grid, deleted it with probability 1/4. So since this number 1/4 is small enough, there's going to be an infinite cluster of connected sites remaining, called the supercritical percolation cluster. And we can run a random walk on this infinite connected component of sites. And I've drawn this random walk in red. So this is another example of random disorder here on the level of the graph. So in each of these cases, the random or periodic environment perturbs the walker on a small scale. But on a large scale, all of these walkers converge to a Brownian motion. So they approximate Brownian motion. Specifically, if you rescale time by n and space by root n, and send n to infinity, the trajectory of each of these walkers converges to that of Brownian motion with diffusivity given by a bar. So it's a standard Brownian motion multiplied by the square root of 2 times a bar, where a bar is some deterministic matrix. And this deterministic matrix, called the effective diffusivity of the Brownian motion, depends in a complicated way on the small scale structure. So it's like in optical mixing, this a bar typically doesn't have an exact formula, and it's typically not sort of a linear average of the small scale system. So in one dimension, you can determine what this effective diffusivity is exactly for most examples of random environments. And in 2 dimensions, in some special cases, like this periodic checkerboard, there's an exact formula for what this effective diffusivity is. It turns out to be the geometric mean of the 2 different transition probabilities. But more generally, there is no exact formula for this effective diffusivity. And one of the key features of homogenization is that we are able to establish convergence without exact formulas, and sometimes without even knowing what this is, just that it's something deterministic which exists.
How do you know a bar even exists? Is it by definition that formula?
So this a bar is
the
usually
solution to that formula.
Yeah, so it's given as a solution of some variational problem, not exactly this. So a priori, like once we establish convergence, all I know is that this is a positive definite symmetric matrix. And afterwards, in some special cases, like in 2 dimensions using duality, we can determine exactly what it is, but in most cases, we don't know what it is.
So in examples you gave, there's like a formula as you change the probability of.
Yeah, like in the checkerboard example, it's the geometric mean for the 2 different transition probabilities, like on the blue squares and the green squares. What I want to highlight is that, so not only in these 3 cases do we have convergence to Brownian motion, but we have convergence to Brownian motion under the same scaling called diffusive scaling. So what this says is that in n steps of time, the walker travels on order distance root n. So all of these random walkers are diffusive. And this diffusive scaling just comes from the fact that if you have a collection of independent mean zero variance 1 random variables, the variance of the sum, because of independence, is a sum of the variances. And the typical size of a random variable is the square root of the variance. So since the variance of the sum is n, the typical size of the sum is square root of n. And so in all of these cases, the scaling is the same as that of a sum of independent random variables, despite the environment having dependencies. So in the main result I'm going to talk about today, we'll have convergence to Brownian motion under scaling which is not diffusive. So that the scaling will be super diffusive, as we'll see. So,
is the rate of convergence like independent of the small scale behavior usually, or?
The rate of convergence is usually faster in the periodic case and sort of a bit slower in the random case and even slower in this other random case. Yeah.
Is it exponential?
It's faster than, well, here it's open to determine the optimal rate. It's expected to be algebraic, but homogenization is typically spoken in the language of PDE. And we can go from these random processes to PDEs by looking at the generators. So if you have any Markov process, so it's a stochastic process which generalizes random walks and Brownian motions, you can define a differential operator called the generator by the following formula. So this is an operator on functions which can either live on the grid or in the continuum, defined in the following way. For example, if we look at our random walks from the beginning of the talk, the generators of those walks are weighted graph Laplacians. So the generator applied to any function f on ZD is equal to the weighted average of the gradient of the function along the edges outgoing from that site. So in the case of the checkerboard, this A function, this transition rate, is periodic. And in the case of the random checkerboard, this A function is random. And you can define the generator in the continuum. And if you have any process, which is a Brownian motion advected by a drift, so that's described by this stochastic differential equation here, the generator of that process is an elliptic PDE, which has a second order part described by, which corresponds to the covariance of the Brownian motion term, plus a first order part, which corresponds to the drift term. So if you have any Markov process, which is a Brownian motion advected by a drift, the generator is an elliptic PDE. So we can go from these processes to elliptic PDEs. And one benefit of this perspective is that roughly showing convergence of the process to a Brownian motion is equivalent to showing convergence of the sequence of generators to the divergence of A bar grad. So in the case where A bar is the identity, this operator here is just the continuum Laplacian. So showing convergence of simple random walk to Brownian motion is equivalent to showing that the sequence of generators converges to the Laplacian. And what it means for the sequence of generators to converge is that the set of solutions associated to these generators converge to the set of solutions associated to the limit generator. And usually this operator, this differential operator, has random or periodic coefficients, but this limit operator has a deterministic coefficient. This effective diffusivity is deterministic. And the theory of qualitative homogenization, developed in the 1980s, gives sufficient conditions for the sequence of generators of random walks in random environments or Brownian motions in random environments to converge. And those conditions are that the transition probabilities are uniformly bounded from above and below at every site, and they satisfy this stationarity condition, stationary and ergodic. So what this latter condition gives you is that if you look at the transition probabilities themselves and average those in larger and larger boxes, that converges to something. So the field of matrices is stationary and ergodic. And we have this pointwise bound, which is needed for this theory to work. So this theory gives these sufficient conditions, and equivalently, so Brownian motions in random environments get given by this matrix A, and random walks in random environments converge under diffusive scaling to limiting Brownian motions. So under this pointwise bound and stationary ergodicity, you have convergence of Brownian motions and random walks in random environments to Brownian motions with deterministic covariance. So this condition here, stationary and ergodic, is quite soft. And without strengthening this condition, we can't really hope to establish any rate of convergence. So the theory of quantitative homogenization says that under the quantitative assumption that the field is mixing, so you can think of this as saying that averages of the field itself converge very quickly to something. Under those conditions, we have quantitative homogenization. And as a byproduct of this theory, we're actually able to relax the pointwise condition on the set of matrices to sort of a coarse-grained condition. And this coarse-grained upper and lower bound covers the cases of the random graph that I showed at the beginning. So if your field mixes very quickly, then you have a rate of convergence for the sequence of generators. And this implies a rate of convergence for the associated diffusion. Yeah.
Is the converse true?
Was it if and only
If you have convergence to a Brownian
If you
motion.
have homogenization, for example, does it imply mixing?
Well, the field can be stationary and ergodic with homogenization. Yeah.
I'm sorry, I wanted to make sure you answered.
What I meant was, under the limit you homogenize,
Yeah,
does the same process also mixes?
it's under the, sorry, I don't understand.
I can ask, yeah.
Okay,
So maybe just a clarifying question. So like, what is like the system that is mixing exactly? Like, what is the action or the dynamics that's?
it's mixing with respect to translation. So like in the random checkerboard example, the blue-green squares, as you zoom out and average, converge to something. So like the transition, in that example, each different colored square had a different set of transition probabilities. And that set of transition probabilities, as you zoom out and average, converges to something. That's what this condition ensures. So it's mixing under the action of
A
translation.
translation should,
Yeah.
that's what I should think of the
Yeah.
action being.
Yeah.
Okay.
Can we translate that to Seurat? Seriously, I mean, do we learn anything? I mean, is that local, is that local homogenization so that we see these colors or?
Yeah, so I don't know exactly how this applies to optical mixing, but maybe this gives a rate of convergence. I'm not. I haven't tried to connect it back. Yeah, so what this quantitative homogenization theory says for the diffusion, for example, for this random graph case, is that, so you have a random walk on this random graph, and the qualitative theory says it has to converge to a Brownian motion. But the quantitative theory lets you couple the random walk living on this random graph to the limiting Brownian motion that it converges to. So you not only know that it converges to something, but you can relate the objects together in a very quantitative way using this theory. So why do we need the field to converge? Why do we need ergodicity or mixing? Well, if the field itself doesn't converge, if, for example, it oscillates between two values, then the diffusion won't converge because the diffusion lives on top of the field. So the field itself has to converge for the diffusion to converge. And in most examples, like in the examples I gave at the beginning of the talk, there is one single relevant length scale above which the environment itself converges. Like in the periodic or random checkerboard, if we zoom out a sufficiently far amount and look at the environment, it looks like it has converged to something. So in all of the examples I gave at the beginning, this is the case. There's just one length scale above which you have convergence. And what I'm going to talk about today, we're going to consider an environment with infinitely many relevant length scales. So the environment itself will never converge, but we're still able to show that the process on top of this environment converges. And this example comes from looking at a diffusion with a random drift. So now for the rest of the talk, we'll be in RD, in the continuum, and we're going to consider a Brownian motion advected by a random drift. So this is described by this stochastic differential equation here. So what this says is that you have a Brownian motion, WT, with molecular diffusivity nu. This is just what this is called. Advected by a stationary random mean zero vector field. So we have some Brownian motion on top of a vector field. So the Brownian motion is moving around randomly, but the vector field is sort of pushing it in random directions. So we have two sources of randomness. One is a Brownian motion and one is this vector field. And physicists were interested in the large scale behavior of the Brownian motion on top of this random vector field. So they looked at sort of the most natural example, which is when the field is Gaussian. So when the vector field at any value is a Gaussian. And they looked at three cases for the geometry of the field. So any smooth vector field can be written as the sum of a potential part and an incompressible part. So they looked at the case where the field is purely a potential or purely divergence-free / incompressible, or fields which are neither potential nor solenoidal. So fields which have both potential parts and divergence-free parts, and also fields which are purely potential or purely divergence-free. So they looked at these three cases for the geometry of the field. And using non-rigorous methods, they predicted that the large-scale behavior of the process depends on several small-scale features of the field. So the first is that they predicted that you should have different behavior depending on whether or not the drift field is isotropic or non-isotropic. And it should also depend on the correlation structure of the field. So how quickly the field, sort of how independent the field is. And it should also depend on the ambient dimension, if you're running a process in 2 dimensions or 3 dimensions, and also on the type of vector field. As I said, if it's potential, divergence-free, or unconstrained. So what's known rigorously is that if you have a field, a stationary random mean zero field, which is either purely a potential or purely incompressible, and your vector field mixes very quickly, then you have convergence to a Brownian motion under diffusive scaling. If you rescale time by n and space by root n, then you have convergence to a Brownian motion with affected diffusivity a bar. Yeah, the question?
Is that a pattern as you increase the dimension? Like you converge these faster or slower? Is there something like that?
So the convergence should be, I think, fastest in 2 dimensions. But I'm not completely sure. Yeah, so in the case where your field is purely potential or purely incompressible, and your vector field mixes quickly, then you have convergence under diffusive scaling to a Brownian motion. And your particle is at large scales diffusive. So the expected mean square displacement of the particle is t. So it's the same as that of a Brownian motion or a simple random walk. And what's known is that if your field is divergence-free, then the effective diffusivity is strictly larger than the molecular diffusivity that you started off with. On the other hand, if your field is a potential, then you should have decreased diffusion.
Also, should we think about these results locally in time or?
So this is about the sort of the large scale behavior. Like you can understand it by drawing the vector fields. So we sample some random vector field. So if your vector field is a potential, if you can write it as a gradient of some other function, and you draw the flow lines of the vector field, it'll be characterized by a set of traps and sources. So if you have a non-random particle that follows these flow lines in t steps of time, it'll travel distance t. On the other hand, a diffusion in t steps of time travels distance root t. So these flow lines are sort of going to are going to have a big effect on the Brownian motion. So the Brownian motion is going to move randomly, but it'll be pushed along these flow lines to these traps. And it'll try to get out, but it'll be pushed back into these traps. And there are going to be enough of these traps that on long time scales, you have a Brownian motion which has a decreased diffusion. the Brownian motion will be slower in the case where you have a potential drift. So these traps decrease the diffusion. On the other hand, if you have a drift which is incompressible and you draw its flow lines, it'll look like a collection of swirls. So there'll be no traps and sinks, and the flow lines will look like a collection of swirls. And if you imagine a Brownian motion on top of this field, like anytime it hits one of these flow lines, it'll be accelerated along these flow lines. And these flow lines will only act as highways for the particle. It won't ever cause it to slow down or be stuck somewhere else. So these swirls will increase the diffusion of the particle. So that's some geometric intuition for why in the incompressible case, you should have enhanced diffusion. So the particle should sort of move faster on large scales than it normally would. And for the rest of the talk, I'm going to focus on this incompressible drift case. And physicists have made very, very precise predictions for the large scale behavior of the process in the case where the drift is incompressible. Yeah.
What happens if F is linear,
If,
where we can compute the solution explicitly? F of so we can compute it's AX, for instance, where you have can calculate the solution explicitly.
where f is linear, so f is mean zero.
F is linear as a function of X. Let's say F of XT is a matrix A times XT.
Mhm. But that's I'm only considering the case where f is mean zero.
It means
So it's not going to push the.
That one
Yeah. So yeah, and like all of these examples, it's sort of mean zero, so it doesn't push it in one direction. Yeah, so in the case where it's a mean zero, stationary divergence-free vector field, they made precise prediction for the large-scale behavior of the process, depending on the correlation structure of the drift. So how quickly the field mixes. So I said before that if the field mixes quickly, then you have diffusive scaling and convergence to Brownian motion. And precisely what that means is that if the correlation of the field between two values decays like x minus y, x minus y to the power of p, and p is bigger than 2, then what they expect is that the particle behaves diffusively. So you have enhanced diffusion, but the particle still moves in t units of time, distance root t. So you have an enhanced diffusion, but you still have, under diffusive scaling, convergence to a Brownian motion. And this is a classical result that you can find in textbooks. On the other hand, if your correlations decay very, very slowly, so you can think of that as the swirls conspiring together, then you have super diffusivity. So the expected mean square displacement of the particle is t to the power of 1 plus gamma. So you have an extra t to the power of gamma as compared to the fast mixing case. So the particle has this algebraic speed up. So this is still far from being proven. There's some rigorous results in 2002 where they show that some version of this quantity scales like t to the power of 1 plus delta for delta smaller than gamma. But this is still far from being proven.
Does P have a lower bound?
So P ranges between 0 and bigger than 0. Yeah.
When you say the classical ones, are those are also not rigorous? Or those are rigorous?
Yeah. So this is completely rigorous.
Okay.
Yeah. But this is not very far from being proven. And the case where P is right between these two regimes is called the critical regime. And what's predicted is that in this case, you have borderline superdiffusivity. So the mean square displacement should scale like t with an extra square root of log t. So it's like that of Brownian motion, except for this extra square root of log factor. And that's what I'm going to talk about today.
Is there an intuition why when P is greater than 2, the variance doesn't depend on P, but when you go below, now you see the dependence on P?
Oh, the variance? You mean this?
Yeah.
Well, there's a constant in front, which depends on P.
In the super diffusive case, you have gamma t to the 1 plus gamma, and
Yeah.
gamma depends on P, but you don't see it in the sub-diffusive or diffusive case.
Yeah, in the diffusive case, you have fast mixing, and so the only effect that the field has is in terms of the constant in front of this. Okay, so different groups of physicists have looked at this problem, and the first group of physicists that looked at this conflated the dimension with this parameter P. They were looking at a special case of a drift field where P was equal to the ambient dimension, and they thought of the relevant parameter as the dimension, and they thought of 2 as a critical dimension, and they predicted the square root of log super diffusive behavior in dimension 2, and diffusive behavior in dimensions bigger than 2. And all the predictions that these physicists made were annealed, meaning they thought that this should only be true after averaging over both the field itself and the trajectory of the particle. And then a couple of years later, another group revisited the problem, and they observed that the relevant parameter was not the dimension, but rather this correlation. So they observed that this critical case, P equal 2, corresponds to the curl of a log correlated Gaussian field in any dimension. So whatever dimension you are in, if you have this object, then you should have the square root of log superdiffusion. Moreover, they thought that this should be valid for every realization of the field. You shouldn't have to average over different samples. So in order to describe precisely what I mean by this, I need to tell you, how do you build a divergence-free vector field? So let's recall that any divergence-free vector field in 2D can be written as the vector which is orthogonal to the gradient of something called the stream function in 2D, and in 3D, the curl of the vector potential. And generally, in any dimension, any divergence-free vector field can be written as the row divergence of a skew-symmetric matrix called the stream matrix. This comes from this Poincaré lemma. And so our case, our critical case, corresponds to taking your skew-symmetric matrix and populating it by entries given by a log correlated Gaussian field. But what is a log correlated Gaussian field? Well, it's a Gaussian function from RD to R. So the value at any site is roughly Gaussian, and the covariance between sites decays like the log function. So it's just a Gaussian field where the covariance of the field is a log function. And the key feature of the log function is that it's scale invariant. So if you take the log function and you rescale space, you get back the log function plus an additive constant. And it's because of this fact that this log correlated Gaussian field appears in a lot of different problems in statistical physics. It's scale invariant. And one way to think about this is the following discrete version of a log correlated field called additive cascades. So start by assigning mean zero random variables to each unit cube. So build this piecewise constant function y0 by assigning standard Gaussians to each unit cube. And then for each integer k, let yk be given by, you sample another independent copy of y0 and you rescale it. So each of these yk, these are all piecewise constant functions that all have the same amplitude, meaning if you look at the value of the function at any site, it has the same law as any of the other functions yk, but they live on different scales. So y0 is piecewise constant at the unit scale, y1 is piecewise constant at the half scale. And if you take all of these different fields, yk, and take the formal sum, then you get something which is approximately a log correlated Gaussian field. And the key takeaway from this example and how you should think of log correlated fields is that log correlated fields have independent constant amplitude noise at every single scale. So they have infinitely many scales that all have the same amplitude. And that'll be the reason why we have superdiffusivity in our problem. But one way to sort of think about this in the context of our problem is that to build this critical drift field, we start with a log correlated field in 2 dimensions, and then take the grad perp of that field and draw the flow lines. So we'll get a collection of swirls. And if we look at these swirls on one scale, it'll look like this. And if we take this picture and we zoom in on, let's say, this spot here, if we zoom into that spot and then look at the swirls, we'll see the same collection of swirls, except living on that scale. So these swirls have the feature that at any scale, you'll have the same sort of looking family of swirls, but just living at that scale. So unlike the random checkerboard where you just had to zoom out one amount, you had to zoom out up to one certain scale after which you have convergence, here you don't have convergence to anything. At every scale, you have the same thing. So it's sort of self-similar.
You don't rescale values?
Sorry?
You don't rescale values when you do?
No. So if we like take here and we zoom out, we see the same swirls, but just on a different length scale. Yeah, so we don't rescale values because at every scale you have the same amplitude. Yeah. So this is how we should think about log correlated fields. And we're going to look at a Brownian motion on top of this random divergence-free vector field. And we want to understand the large scale behavior of the Brownian motion. So different groups of mathematicians have looked at this problem, and some progress has been made. So all groups before us were just looking at the case where the dimension was 2 and your field was exactly a log correlated Gaussian field. So this first group, Toth and Valco in 2010, showed that if you average over both the field and the particle, you have superdiffusivity. So you have this extra log, but they didn't identify the correct square root of log rate. And then in 2021, Cannizzaro, Hauschenschmidt, and Toninelli showed the square root of log superdiffusivity, but up to log corrections. And then a couple of years later, Chutzi, Giorgio, Morphy, Otto, and Wang showed that for any molecular diffusivity nu, the expected mean square displacement after averaging over both the field and the particle scales like square root of log t, but up to constants to c, depending on this nu, depending on the initial diffusivity of the Brownian motion. And all of these results are annealed, meaning they involve taking 2 averages. They also use exact Gaussianity. So the field needs to be exactly a log correlated field. So earlier this, I guess last year now, with my postdoc advisor, Scott Armstrong and Tuomo Kuusi, we showed the following result. So take any field, which is approximately a log correlated field, an arbitrary dimension, and take the curl of it to get a divergence-free vector field, and then run a Brownian motion on top of that field. So for almost every realization of the field, under superdiffusive scaling, one has convergence to Brownian motion. So this differs from the scalings that we saw before by this extra square root of log factor. So you have convergence to a Brownian motion. Also, there exists a deterministic constant independent of the initial diffusivity of the Brownian motion, such that the expected mean square displacement of the particle, if you rescale by t squared of log t, converges to this constant c star. So this is independent of the molecular diffusivity. So this is the first result, which shows quenched superdiffusivity, which shows superdiffusion for almost every realization of the vector field. And also, we showed that this rate of superdiffusion, this number, is independent of the nu. Yeah,
Yeah, I think the natural question would be to study what happens in the vanishing diffusivity.
Yeah, yeah, it is a natural question. So there are a lot of constants here which depend on nu. Like we have rates of convergence which depend on nu, and we can't really take nu to 0. Yeah. But what I want to point out is that this was conjectured in the physics literature. And actually, in the case where you have a field which is exactly a log correlated Gaussian field, then physicists have predicted an exact formula for the C star. And we are able to compute that exact formula and verify their predictions. Like it's some function of pi and the gamma function. So physicists predicted that this is the case, but they didn't predict convergence to the Brownian motion. That's something new. Yeah.
Can you elaborate on what you mean by approximately logarithmic motion?
Yeah. So the field just needs to have tails like the Gaussian, like the Gaussian. Like the value of the field at any point doesn't need to be exactly Gaussian, but it just needs to have Gaussian tails. That's roughly what I mean by that. So after proving this, we were able to understand where the superdiffusion comes from. So we after writing the proof, we were able to come up with a heuristic for the superdiffusion. And the idea is that the randomness of the Brownian motion destabilizes the trajectories of the ODE flow at every single scale, causing an enhancement. So the way we think about it is that at the unit scale, we have unit scale swirls of this field. So along the swirls, the particle sort of moves very, very quickly, since sort of in t units of time, you move distance t along the swirls. But there's some randomness. So it sort of swirls along, but because of the randomness, it'll from time to time jump from one swirl to the next. And this jumping between swirls, if you zoom out, looks like a Brownian motion on a slightly larger scale. So this diffusion causes it to jump between swirls of the same scale. And if you zoom out, this jumping between swirls looks like a diffusion on a larger scale, but an enhanced diffusion, because along the swirls, it moves very, very quickly. And I keep emphasizing that this log correlated field is self-similar. So if you zoom out a bit, you'll see swirls on a slightly larger scale. And so this process will repeat. So there's going to be this infinite recursion. And this causes an enhancement of the diffusion at every single scale. So this is what it is sort of in words. And now I'll show a simulation, a hand-drawn simulation of what happens. So I've drawn here the swirls at the unit scale. And this blue dot is the Brownian particle. So it's a Brownian motion, so it moves randomly, but it'll be pushed along the swirls. And then it'll jump to another swirl. And then it'll be pushed along the swirl, and then it'll jump to another swirl. So if you take this picture and you zoom out a bit, you'll have swirls at the next scale. And if you forget about the scales, the unit scale swirls, it just looks like a diffusion on that scale that's slightly faster. And so this process is going to repeat. And what happens is this happens at every single scale. You have the diffusion pushed along the swirls, and it will jump from swirl to swirl. And at every single scale, you have an enhancement of the diffusion. And this infinite cascade of enhancements causes the square root of log superdiffusivity. So it causes this diverging superdiffusivity. So to actually prove this, we work with a generator of the process. So the generator of the process is the following elliptic operator. So it's a Laplacian plus this first order term. And since this f is divergence free, we can express f as a row divergence of a stream matrix. So we can write the operator as exactly the divergence of some matrix times a gradient. So we can, in other words, we can express the operator as something which is a pure divergence form elliptic operator. And the reason for doing this is that this now allows us to use techniques from the homogenization of such operators. And the super diffusive invariance principle is equivalent to showing that this generator is close to the Laplacian. So we want to show convergence of Brownian motion. And so equivalently, we can show that this generator is close to some multiple of the Laplacian. We want to show specifically that on length scale 3 to the power of r, it's close to square root of r times the Laplacian. This is sort of equivalent to the square root of log super diffusivity in the geometric scale. And the idea is to study how the operator changes scale by scale. So just like in the heuristic with the diffusion, we want to understand how the operator changes scale by scale. So we start with writing our log correlated field in this way. So we write it as an infinite sum of independent Gaussian fields which live at length scale 3 to the power of L. So just like with the additive cascade, we can express anything, any log correlated field as an infinite sum of fields which all live on different scales. And below length scale 3 to the power of n, these fields above that scale are essentially constant. And so we can ignore them in the operator and express the operator on length scale 3 to the power of n as the operator where all of the fields above that scale are just removed. And by the existing theory of homogenization, we know that an operator of this form has to converge to something. And since the field is rotationally invariant, the only thing it can converge to is a Laplacian. And now our problem reduces to studying the constant in front of the Laplacian. So we want to show that this constant in front of the Laplacian has the correct superdiffusive growth. And we do that by writing down a recursion for this affected diffusivity, this S bar n. So assuming that things converge very, very quickly, we can write the operator at scale n plus k as sort of the sum of the fields up to scale n plus the fields between scale n plus 1 and n plus k. And the fields up to scale n converge to this multiple of the identity. And then assuming that this multiple diverges, so that's what we want to show, but assuming that it diverges, we can pull it out. And what we're left with is something which is very, very close to the Laplacian. So something which is the identity plus a very, very small term. And we can analyze operators which are very, very close to the Laplacian. We can do like a first order expansion. And this determines this constant C star. So it determines, yeah.
Is this for all k?
So we at some point need to optimize what we choose k as. But this is very rough. So like k needs to be a log n. Yeah, but assuming we can do this, assuming we can pull this out, and what we get at the end of this is that the effective diffusivity at scale n plus k is the effective diffusivity at scale n plus this increment term. And this can be solved exactly or approximately, and this gives you the square root of log superdiffusivity. And it's precisely this perturbative problem that allows us, like the solution of this perturbative problem gives us this constant C star, which is the universal constant which the physicists predicted. So there are a lot of difficulties to make this precise, which I'll skip over. But what we show after all of this is we have a super diffusive invariance principle. And what we get from the proof is that this super diffusivity occurs because of homogenization happening not just at one scale, but at infinitely many scales. We have this infinite cascade of homogenization. And this approach where we study how a model changes scale by scale seems very flexible and could work for other problems. And we expect that our methods are a starting point for tackling other problems with infinitely many length scales. And we have some specific extensions But I think I'm out of time, so I'll just leave this slide up. Thank you.
Are there questions or comments?
Two questions actually. First, is it relevant to study F that is time dependent?
Yeah, so that's this bullet point.
And then follow-up question, can you introduce feedback to the system saying F evolves to some equation, and then you would probably get, say, homogeneous fluid equation type thing?
Introduce what? I didn't hear that.
Say F also evolves,
Yeah,
and then now it's not passive, but it's active, and then you solve for it.
yeah, that's a possibility. We haven't looked at that, but
So was for some of the results earlier when you were talking about F being like divergence type.
yeah.
What would happen if you like, do you expect the results to still hold if you just replaced F with something that was like divergent, like sort of like a divergence vector field, but not actually divergent? So
Like something approximately.
yeah, like you could perturb a divergence vector field, it's still gonna be it's still gonna be kind of character, like dynamically it'll be kind of the same thing.
Yeah.
Um,
Yeah, so I think that's a very difficult problem.
okay, so you think that's like completely
Yeah.
inaccessible?
Yeah, so the key feature of this divergence-free vector field is that you can like pass it into the equation
Yeah.
and then just study an equation in divergence form. And if it's not in divergence form, then the set of techniques are completely different. So you'd have to, yeah, it'd be difficult. Like, I mean, one reason why this is difficult is that it's still open to determine what happens if your vector field is not divergence free or not a potential. If it's something which is just like white noise, it's not known what happens in 2 dimensions. In 3 dimensions, there's something is known, but in 2 dimensions, nothing.
In any of these contexts, do these homogenization approximations have interesting or meaningful subleading errors?
Yeah. So in our main theorem, we determined this constant C star, which is like the first order term in the expansion. That constant is deterministic, and we think that there should be a second order correction, which is random. And we almost determined the second order correction, but there might even be a full expansion of terms. But that's beyond the reach of what we can do right now.
Well, I'm just curious about this last bullet. So what would be what kind of diffusion term would you be looking at?
Yeah, so in this last bullet, we're sort of considering this random surface called Louisville quantum gravity. And what we want to do is we want to understand the Hausdorff dimension of the random surface by understanding the diffusion on top of the random surface. And like how subdiffusive the process is on top of the random surface should indicate what the Hausdorff dimension of the surface is.
So you'd be doing a random walk on the.
Yeah, you're doing like a Brownian motion on top of this random surface and understanding the properties of that Brownian motion.
Can you determine the Hausdorff dimension?
No, not yet. Maybe in 2 years.
Question about this isotropy and non-isotropic, can you comment on that? Why is it so? Is it like a faster rate?
Yeah.
Non-isotropic case?
So in the heuristic that I gave, we were able to use isotropy to reduce the problem to studying one parameter, this effective diffusivity. In the case where you're not isotropic, you can't make that reduction because you don't have full rotational invariance. And it's expected is that the theorem should be different. You shouldn't have square root of log superdiffusivity, but log 2/3 superdiffusivity. And we still can't prove that, but the idea is that if your swirls are not rotationally invariant, and you're like more likely to go up and down than left or right, then you'll have like log 2/3 superdiffusivity in the vertical direction and log 1/3 in the other direction. Yeah.
At the beginning of your talk, you said connection with turbulence.
Yeah.
How would you connect this to turbulence?
Yes. So I don't know much about turbulence, but what I do know is that in the first paragraph of all the physics papers, they write, motivated by turbulence, we will study the passive tracer model, which is, yeah, the passive tracer model is just a Brownian motion in a random divergence-free vector field. And it's supposed to model a tracer particle in a fluid.
How about the application to PDEs?
Yes.
The application to.
Well, for example, Kolmogorov's theory of turbulence.
Yeah, there's no direct application. I mean, this could be thought of as an example of a turbulent fluid, but there's no connection beyond that.
I was just curious, you mentioned like the physicists had this like prediction for the constant C star and the
Yeah.
log term, like where, what kind of, was it just from simulations or they had some other kind of
No,
heuristic?
they had like very, very rigorous, non-rigorous methods. Like they were able to determine the exact constant, and like we proved that it's that exact constant using very, very different methods.
I see, so it was some
Yeah.
sort of analytic derivation.
Yeah, but no simulations because there are like logs here and you can't really simulate logs.
How accurate are the hand simulations?
Or which simulation?
The hand simulations you showed.
Drawings.
Oh, yeah,
Your
they're
sketches.
very accurate. Took me like 2 hours with the iPad.
Sometimes in PDs, this super diffusion or subdiffusion refers to powers of Laplacian.
Mhm.
Instead of one, if you have a power of Laplacian greater than one or less than one. So in your case, the operator was converging to Laplacian plus drift.
It was converging to the Laplacian.
Okay, Laplacian, is it possible to fix a value of P but then change the functional setting so that it converges to Laplacian to some power and you still get super diffusion? For P that is not super diffused, or say P.
To fix the function. Yeah, I'm not sure how to get that. Yeah.
So, other questions or comments? Then let's thank Ahmed again.